Computer. So good afternoon, everybody. So I'm Gerard O'Reilly. So what we're going to be looking at is just some of these seminars that we're organizing here in Pavia at the Rose Center. So these are just some presentations that some of the PhD students and other researchers in the general area have been giving over the past few months, let's say, on their research and some of the things that they've been looking into. So the presentation should generally be about 1 hour, depends on how quick Derek is. But that's generally the idea we try to stick to. So the structure will be the presentation first, and then some questions and discussion afterward. I would just ask people to keep maybe their microphones and cameras, if you want, keep them off, so just we don't have any interference or interruptions during the presentation. A reminder then is that, as I just mentioned, this presentation will be recorded, and later on today I'll upload it onto YouTube and share on LinkedIn and so on. So if you want to catch up on anything or have a look at anything again, it'll be available online. So today's presentation is by Derek Rodriguez. So Derek is going to give us a presentation on a probabilistic strong floor motion duration model for the seismic performance assessment of non-structural building elements. So I'm quite interested to see what Derek is going to tell us about this. So Derek, the floor is all yours.
Yeah, thank you so much. Can you see the slides clearly?
Yes. Perfect.
Okay. Okay, so well, thanks a lot to everybody for being here, the ones that actually connected. As you can know, many of you already know me. For the ones that you don't know me, my name is Derek Rodriguez, as Gerard said. I'm a PhD student at Pavia, at IUSS Pavia. And basically what I'm going to present here is a part of our research that the non-structural elements research team has done in the last few months. So the name of this presentation, the title is a probabilistic strong flow motion duration model for the seismic performance assessment of non-structural building elements. So this is the outline, the different things I'm going to be talking about today. This is basically, we're going to have an introduction, then we're going to have a motivation to see why we're doing this, basically. Then I'm going to talk about the development procedure for the probabilistic model. Then I'm going to present you the numerical results that were obtained. And then I'm going to speak about the construction of the probabilistic strong flow motion duration model specifically. And then we'll end up, of course, with some conclusions that can be drawn from the investigation itself. So, introduction. So basically, there is currently no information or research on the characteristics and duration of strong shakings of structures given a seismic event. What do I mean with this? Basically, what I mean is that we don't know, there's a lack of information regarding the amount of time a structure actually shakes during and after an earthquake. I mean, we know a lot about the response. We know a lot about, you know, the stiffness properties and the damping and a lot of things, but there is no research about the duration that the structure actually shakes, because it's not necessarily the same as the duration of the ground motion, as you can imagine. So as part of our research, part of the research that we're doing right now in the team, specifically for my PhD dissertation, we are in the need of using synthetic fluid motions. And for the ones from the ones of you that are familiarized with signal processing techniques, usually when you generate synthetic accelerogram, a very important parameter is the duration of what is called the strong motion duration of the accelerogram, let's say. So, for example, when you generate synthetic ground motions, usually you use the strong ground motion duration. That is a very well-defined parameter because it has been extensively researched by seismologists. But in the case of fluid motion, we don't have this kind of information. So this is what this investigation focuses on. So the term strong fluid motion duration is going to be also used, the abbreviation SFMD, will be adopted herein to refer to the duration of a strong shaking of a structure given a seismic event, defined analogously to the Iris intensity definition of the strong ground motion duration. We're going to talk about this in more detail later. So regarding the motivation, I mean, why are we doing this? I mean, why do we want to use synthetic motions? Why do we need this type of model? Well, basically, the global topic of my research is to develop a methodology to quantify seismic performance factors for non-structural elements. So currently, the FEMA P695 standard in the United States addresses the determination of seismic performance factors, but for seismic fault resistant systems. So in other words, for structures. It doesn't talk, or it is not for non-structural elements or secondary systems, as they're called in different parts. So as many of you can imagine, the performance evaluation of non-structural elements entails a series of challenges that are not present in the performance of traditional structures. So this makes that currently there is not an equivalent FEMA P695 framework to quantify seismic performance factors for non-structural elements. And this is a big issue because this makes that the seismic performance of non-structural elements designed according to force-based procedures uncertain at best currently. I mean, usually the most developed codes, let's talk about, for example, the ASC 716. They have seismic performance factors for non-structural elements. However, many of these factors, their origin is very dubious. I mean, they were not developed with a strong theoretical background. Let's say many of them are basically based in engineering judgment, and other ones are from empirical nature, but using data sets that are very small, basically. So this is a main issue right now with the design of non-structural elements, with the force-based design of non-structural elements. So what are these main challenges that I was speaking before about the seismic performance assessment of non-structural elements that are not present in the seismic performance assessment of structures? Well, basically, there's 4 of them that I consider that are the biggest ones, maybe. And so the first one is that the ground motions are filtered by the seismic fault resistance systems of the supporting structure. Therefore, this adds an additional layer of complexity and uncertainty to the determination of the seismic demand of non-structural elements. So as the ones from you, the ones of you that are familiarized with the non-structural elements, usually what is done in the common practice is that we use fluid motions for the design or evaluation of non-structural elements. And these fluid motions are basically the resulting accelerations of a particular story giving a seismic a ground motion analysis. That's a nonlinear time history analysis. So as you can imagine, having this additional layer of analysis is very complicates things a lot, basically. And then we have that also non-structural elements archetypes possess a higher variability in comparison with structural systems due to the large number of intended uses they can have. If you imagine, for example, structural systems, in the last decades of earthquake engineering, I mean, the community has come around with many systems, but at the end of the day, they look alike a lot, you know. Like, for example, you can have a moment resistant frame, you can have a shear wall building, or you can have a cantilever structure or whatever. But I mean, at the end of the day, the geometric characteristics of these systems, they don't differ a lot. I mean, they're more or less consistent, let's say. With non-structural elements, we don't have this. It's much more complicated because, for example, you can have pipe rings for a piping system in a ceiling, and then you can have partition walls, and these two have completely different layouts, completely different geometric characteristics, stiffness characteristics, and this complicates things a lot as well because basically it increases the variability of the geometry of the systems, and this is not an easy issue to deal with. Then as a third point, we have also that there is currently no information available to establish non-structural total damage uncertainty. For the ones from you that are familiarized with FEMA P695, they actually specify very clearly the beta, that is basically the normal standard deviation for the total damage uncertainty of the systems. And this is something that is a very robust way to assess performance. I mean, if you want to do you want to assess performance in a very robust way, you need this type of information. And this is not, it has not yet been developed for non-structural components, and there's not much information about it. So this is also an important issue. And finally, also we have that non-structural elements have the characteristic that they are much more vulnerable to at lower seismic intensities that their structural counterpart, which means that usually when you assess performance of non-structural elements, it's very important to actually assess the performance at different limit states. This is not the case for structures usually, because, for example, the FEMA P695 basically assess the performance of the structure just against collapse. So they just care about the collapse. And that is basically the main criteria you use to assess performance. When you're talking about non-structural elements, we cannot do this because, I mean, there is a lot of different limit states that wants to be checked given the high vulnerability that these systems have at different seismic intensities. So usually this requires that different seismic hazard levels must be considered for this. So, well, some of you could say, well, you could just basically apply a brute force approach using the FEMA P695 and just, you know, do all the analysis for all the structures for which you want to quantify performance of non-structural elements, and it should more or less be the same. Well, yeah, you can do that, but the problem with doing that is that the amount of computer power that you need to do that, it makes the process unfeasible because it's just way too many analyses. To give you an example, for example, if you want to say, if we will want to assess the performance of non-structural elements in a 100 reinforced concrete building population that possesses, like, for example, an average numbers of stories equal to 4, that is like is pretty standard. And we use the FEMA P695 ground motion set that is constructed with 22 records. This would mean that the total number of analyses that we will require will raise to the order of 11,000 per hazard level. So let's say that this is per hazard level. If you want, for example, to assess 3 different limit states, then we're talking about 33,000 analyses more or less, because we have to do, first of all, the 100 buildings times the 22 records time histories. And then after that, take the output from this analysis and use this output as the new input for a new set of analysis of the non-structural elements that it would be with the 100 buildings times 4 stories times the 22 records. So as you can see, things get complicated very fast, and this makes the process like very difficult to deal with, because it will basically take a lot of time for people to, and a lot of computer power to just assess the performance of a non-structural element system. So basically a different approach is needed to make this process less laborious. This is basically the general framework that we are proposing for the development, for the establishment of seismic performance factors of non-structural elements. Basically, this is the same methodology of the FEMA P695, with the exception that we have an additional phase, that is the phase number 2, that is called established seismic demand. And this phase is critical because basically this is where the main difference between the performance assessment of non-structural elements and building structures is. And this is the part in which this current research topic is, because we want to use synthetic fluid motions that are going to be selected in a way that they're representative of the whole building population in order to simplify them and reduce the number of analyses. And for this, we actually need the strong fluid motion duration. So that's why we're here right now. So development procedure of the probabilistic strong fluid motion model. What you're seeing here basically is a flow chart that basically summarizes the procedure that we follow to develop this probabilistic model. We have 3 phases that in which it can be divided. The first one is called development of building population. That basically is the development, as the name says, of the building portfolio that we're gonna that we considered for the evaluation of the strong fluid motion duration. Second, we have the ground motion selection and scaling. That is basically the selection of all the ground motions and the different return periods that we're going to consider also for the evaluation and for the development of the probabilistic model. And finally, we have the analysis procedure, in which basically we perform all the analysis and we do all the post-processing of the results in order to get to try to understand how this parameter behaves and what can we do with it. So in the first phase, that is the development of the building population, basically 100 reinforced concrete frame population was considered, mainly because this type of structure archetype is very used in Europe in urban regions, especially for housing units, and it has been documented thoroughly in exposure investigations. And basically, this population was generated by means of Monte Carlo simulation. And also, these buildings, once they were generated, they were designed according to Euro Code 8 in a site close to Casino, Italy. And the range of fundamental periods ranges basically between 0.3 and 1 second. So as you can see, even though that we're just considering moment resistant frames, let's say, the range of periods is quite wide. So it encloses also period values that are typical of other seismic fault resistance systems. So this is an important characteristic that this building portfolio has. What you're seeing here, this is the histogram of the building fundamental periods of the population. And you can see also in there the median and the median plus minus 1 standard deviation, just to see where we're standing, right, basically. Regarding the ground motion selection and scaling, a site close to Casino, Italy was selected. This site has the characteristic that has a PGA equal to 0.21 G for a 10% exceedance in 50 years. That is the same as 475 year return period. And is basically was selected also because due to this the characteristics of the site, it can be considered representative of a medium to high seismicity far field site in the European region. So this is a very important characteristic that this site has. As I was also explaining before, since we are dealing with non-structural elements, we are in the need of also considering several hazard levels because we want to assess performance of the non-structural elements at different limit states. So 9 different return periods were considered, namely 30, 50, 70, 100, 140, 200, 475, 975, and 2,475 year return periods respectively. And the selection of the ground motions was based on a conditional mean spectrum. 3 conditional periods were considered, 0.2, 0.5, and 1 second, and they were selected based on the aging value analysis of the building portfolio, basically in the period, based on the period histogram that I showed you before. And 20 records were selected per return period. A very important thing that I want to talk about is about adjustment that had to be done to these records, and it's this last bullet point that you see there. Basically, the records were lengthened with 10 seconds of zero acceleration values at the end in order to allow structures to freely oscillate to its final configuration. This, in this case, is very important because many of you know already probably, when you perform a nonlinear time history analysis of a structural numerical model, let's say, it happens almost like 100% of the times that when the analysis is finished, the structure actually has not stopped moving or shaking, because this is basically just a numerical model, which means that the analysis will run as far as the ground motion actually runs, or you know, as the ground motion goes, basically. So in order to assess the strong fluid motion duration, we need to be sure that the structure actually oscillates completely to its final rested configuration, because otherwise we cannot be completely sure if this residual movement of the structure after the ground motion is finished is strong enough or not to actually impact the strong motion duration of the accelerograms. So this was an important adjustment that had to be done to other records in order to be sure that we're not going to have any issue with this. So now regarding the analysis procedure, that is the third phase of the framework, basically. It consists of performing all the analysis, as I said before, and doing the post-processing. That is what I'm going to speak about right now. Well, first of all, the first step was to filter all the free motions, because there is, depending on the software that it is used to run the analysis, it happens a lot that depending of the numerical integration scheme that is used for the time history procedure, it happens that there is a noise present in the final accelerograms. And this noise affects heavily the calculation of the strong fluid motion duration, sorry. So because of this, these motions needs to be filtered in order to remove this noise, this unwanted noise. So basically all the fluid motions were filtered using a low pass filter with a cutoff frequency equal to 25 Hertz. And this frequency was selected basically because since the fluid motions are basically filtered by the structure, the frequency ranges that we want to keep are the ones that are close to the actual fundamental frequencies of the supporting system, because they will damp a lot when you're far away from the main periods of the main frequencies of the structure. So this 25 Hertz was basically selected in order to be sure that we're not getting rid of the good stuff. Let's say we're getting rid just of the unwanted noise. And regarding now to the strong fluid motion duration, as I briefly mentioned before, the strong fluid motion duration was defined herein analogously to the Arias intensity definition of the strong ground motion duration, which basically is the difference between the time at which the 95% and the 5% of the total energy of the accelerogram is reached. And the total energy is basically represented by the IUSS intensity parameter, that is basically pi between 2g times the integral of the square acceleration from 0 to the total duration of the record. Also, a new parameter was also defined, that is, it was named the strong motion duration ratio, which basically is defined as the ratio between the strong fluid motion duration and the corresponding strong ground motion duration. So basically, what these parameters gives us is the type of information that this parameter gives is whether the strong fluid motion duration is longer or shorter than the corresponding strong ground motion duration. In other words, this parameter tells us if we have an amplification of the duration in the structure with respect to the one of the ground motion, or if we have a shorter duration instead. This is an example of how the strong fluid motion duration and the strong motion ratios are calculated. Basically, what you have in here basically is a 4-story building that is one of the buildings for the building population. And what you have in the middle plots are for the base, you have the ground motion, obviously, because there is no story in there. And you see the accelerogram of the ground motion there. And you see the strong ground motion duration that is equal to 12.58 seconds. And to the right, you see the evolution of the Arias intensity with time, basically. And you see where the T5 and T95 are calculated, which corresponds to the 5% and 95% of the Arias intensity. And for the now for the stories of the building, we will have the fluid motions that basically you see the first, second, and third story. And third story is there's a 3-story building. Sorry, I don't know what to say for a 4-story building. And you see that the strong fluid motion duration is calculated the same way, but using the fluid motion basically. And also the strong motion duration ratio is also in there, that is calculated as the ratio between these strong fluid motion durations and the corresponding strong ground motion duration at the base of the structure. So for this particular case, you can see that we have more or less a strong motion duration ratio of 1.17, more or less in average. So almost 20% increment, let's say. So numerical results. This section basically shows the main numerical results that we obtained for this investigation. And this is a very difficult plot to explain, actually. And this is something we're dealing right now. This plot, basically, what it has is, you see in the horizontal axis, it has all the return periods that were considered, the 9 return periods that were, for which we have selected ground motions. And in the vertical axis, we have what is called a mean coefficient variation. So what do I mean with this mean coefficient variation? Basically, each dot of the plot at each line, at each vertical line, represents one building. So basically, each stripe of lines, each vertical stripe of lines has 100 dots, because as you remember, we have 100 buildings in a building portfolio. And each one of these dots, basically, each of the structures, as I mentioned before, for each return period were analyzed using 20 records for that return period. For each record, we have one strong fluid motion duration per each story of the building. So basically what we did is, in order to investigate firstly, was to see if there was an important variation of the strong fluid motion duration along the height of the building. So what we see here as mean coefficient of variation is the coefficient of variation of the strong fluid motion duration along the height of the building. So this tells us if the strong fluid motion duration varies a lot or not along the height of the building. And it says a mean coefficient of variation because it's the mean coefficient of variation for the 20 records. So that's why we only have 100 points, because it's 1 point per building, and each dot represents the mean coefficient of variation for the 20 records. So basically, as you can see from this plot, the mean coefficient of variation varies. It doesn't vary significantly. I mean, basically, we have that it ranges between 0.02 and 0.08 for most of the cases, which is the same as saying 2% and 8%. So this means basically that we don't have an important variation of the strong fluid motion duration values along the height of the building. And that is something you can actually see again in this example that I showed you before, because if you see there strong fluid motion duration values in each story, you can see that they don't vary significantly. We have 40.65 in the first, we have 40.89 in the second, we have 40.78 in the third. So as you can see, it's more or less constant, we can say. So this plot summarizes that in order to see how it behaves across the whole different return periods. And that is what it says in here. Basically, each dot on the graph represents the mean coefficient of variation of the strong fluid motion duration of each building for the 20 ground motions. The values, as I already mentioned, ranges between 2 and 8%, which means that there's not an important variation of this parameter along the height of the building. So because of this, the variation of the strong fluid motion duration along the building height was neglected, and the probabilistic model was built using only the mean strong fluid motion duration along the building height. The second set of results, this is basically a summary of all the results that were obtained regarding the strong fluid motion duration of the buildings. Basically, what you're seeing here are 9 3D plots, each one for each return period. And each one of them plots the strong fluid motion duration in the vertical axis against the strong ground motion duration and the building fundamental period in the bottom. So basically, it describes the relationship between these 3 different parameters. And the green surface that you see also in there is a plane that was fitted to the data. And you can see also the coefficients of determination that for each one of this regression models, let's say. So I'm going to talk about that in this slide. So basically, a plane was fitted for each data of each return period by means of ordinary least squares multivariate linear regression. The high values obtained for the coefficient of determination, they range between 0.78 and 0.9. As you can see in this plot, for example, we have 0.84 in the first, 0.9 in the second, 0.85 in the third, and so on and so forth. So we can see that these values are very high. So this basically demonstrates that the relationship between these 3 parameters can be accurately described by the equation of a plane. And a very important observation from the data here is that across all the return periods, the strong fluid motion duration increases with both the fundamental period of the structure and with the strong ground motion duration and with the corresponding strong ground motion duration. So, okay, that data looks very nice and everything, but I mean, what can we do with that? Because that is very deterministic. We need something in order to be able to estimate probabilistically the values of the strong motion duration, because that's what is needed for the synthetic generation of fluid motions. So that's what I'm gonna talk about in this few slides in this section. So what you're seeing here basically is an explanation of how the model is built. Basically, what you in the left side plot in the graph, what we have is more or less like a slice of one of the surfaces that I showed you before. So we have in the horizontal axis the fundamental period of the structure, and in the vertical axis we have the strong, not the strong fluid motion duration, but the strong motion duration ratio. So the ratio between the strong fluid motion duration and the strong ground motion duration. So basically we're condensing the data in the 2D plots. And as you can see there, the plot is basically made of several vertical data points, vertical stripes of data points. And each of these stripes represent one building, basically, of the population. And each of the dots of the vertical stripes represents one ground motion. So in order to develop the model, what we are going to do is to fit a probability distribution to each of these vertical stripes to try to find later on a regression model that can give us an estimate of the moments of that particular distribution. So what we're seeing in there, in the left plot, we see a vertical green line. Well, it's not vertical, it's actually a probability distribution. Is basically a fit for that particular line of points. And that is what you see in the right side plot, is that distribution and that set of points has been extracted and plotted in the right separately to demonstrate what we're doing. Basically, you see in there the histogram for that particular stripe of points, and you see a log normal fit of that histogram. So this is for a 470-year return period, because I mean we did this all for all the return periods, but I'm not going to show you all of them because that would be crazy and that would consume a lot of time. So I'm just showing you this as an example. And you can see that the period of that particular building was 0.41 seconds. That is indicated in the upper side of the right-hand graph. So next, what you're seeing here, basically, we did the same for, no, first of all, we want to see which is the best probability distribution that we can use to fit the data, because I mean, that is a hot topic, you know, like there's many probability distributions, many of them have different properties. And it is desirable to know which one is the one that maybe can give us a reasonable approximation of the data. So in order to have a first taste, you know, to see initially what probability distribution would have sense, we plotted different histograms of many of these data stripes for different term periods and see what shape the histograms had. So as you can see from here, these plots, there's one plot per each return period, and each plot basically takes a random building and plots the histogram. So to see how the data looks, basically. So from this data, basically, there is two things that we can notice. First of all, is that it looks a bit skewed to the right, as you see in most of the cases, at least. Not in all of them, but in most of the cases, it looks like a bit skewed to the right. And also, of course, the values are positive because we're talking about the strong motion duration ratio. There cannot be negative values. And as many of you know, there is a very common probability distribution using earthquake engineering, which has these two characteristics, and it's the log normal distribution. So, as this is what I was explaining before, in most of the cases, the data seems skewed to the right. And because of this, the log normal distribution, which is widely used in earthquake engineering, was selected as a first candidate to fit the data to see if it has sense, maybe. So, but the problem with this also is that, of course, when you fit a probability distribution, you need to assess the goodness of fit, because you cannot just fit a probability distribution. That's it. I mean, that would be a terrible practice. So, the goodness of fit that needs to be assessed. So, how to do this? Well, there are several ways of doing this. You know, there's hypothesis testing, there's probability plots. There are a lot of ways in literature for which you can evaluate the goodness of fit of a probability distribution. Lilliefors test could be considered, but in this case, it wasn't considered not adequate, because I mean, the problem with hypothesis testing is that in order, if you have a very small sample size, it's very difficult for the hypothesis test to actually reject the hypothesis. So it is not a good practice to use hypothesis testing when you have a very small sample. And since the sample size in this case is 20, because we have 20 dots per vertical line, because it's one dot per ground motion, it was not considered a very robust approach. So it was determined that a better approach would be to use probability plots. And that's what we see in this slide over here. Basically, we have that per each of the buildings that I showed you before in the histograms, we did a probability plot of the log normal fit to see how the data looks. And as you can see, basically each plot has in the horizontal axis the theoretical quantiles from the distribution. And in the vertical axis, we have the order, the sorted values, let's say, of the strong motion duration ratio sample. And what we need to have in a probability plot to be sure that the data is actually approximated well by the distribution is more or less a linear relationship. As we can see, at least for the buildings that we are sampling, the data doesn't look bad. I mean, it looks that the log normal distribution can accurately approximate the data. But we have a problem with this also, another problem. That is that we are doing this just for 9 buildings. And we have 100 buildings times 9 different return periods times 20 records per each one. So we need to assess this for the whole ensemble of data. And the sample is very big. So I mean, and the problem with the probability plots is that their evaluation is visual. Probability plots, I mean, they're in the end of the day, their evaluation is quite subjective because it's something that you need to perform visually. You need to see data. You need to see if it is more or less linear. So it's difficult to automate. So I mean, what can we do in order to efficiently evaluate this goodness of fit for the whole ensemble of data? So what we did is that we constructed what we call error plots, and to assess if the whole ensemble of data. And the error plots basically are constructed with a parameter called the error ratio, which is defined as you can see in there. Basically, the error ratio is the ratio between what is called SMDRI, that is basically the strong motion duration ratio of the ETH value of the strong motion duration ratio sample sorted in ascending order. So basically, we sort the data in ascending order, and each value, and we go assessing the data point by point in ascending order. And the TQI is the theoretical quantile from the fitted log normal distribution, and also it has the subscript I because it's also the theoretical quantile at the same step of the sorted values of the complete sample. So I know this is confusing, but I mean, there's not a easy way to explain this. So basically what this ratio says is if this ratio is equal to 1, it basically means that the strong motion duration ratio value is accurately predicted for that particular quantile. If it's more than 1, it clearly indicates that it's overestimated, and if it's less than 1, it's underestimated. So what we did is that now we constructed these plots per each return period to evaluate the whole ensemble of data. Basically, we have what you see in there is a set of points that have a vertical error margin that is represented by a vertical bar with two caps in the extremes. So as you can see, for all the return periods, the dots that you see in there represent the mean error ratio. So we calculate the error ratio for all the sample. And the vertical error margin represents the standard deviation. So as you can see, for all the populations, the mean error ratio is 1, which means that we are predicting the mean accurately for most of the data. And also this error margin is very small for most of the the fundamental period range. You can see that for most the range of the fundamental period range at all return periods, this standard deviation or margin ratio, call it whatever you want, is in average more or less than 5%. Because I mean, this is not, I say 5% because this is standard deviation, but because the mean is 1, this standard deviation is very close to being the coefficient of variation in the end of the day. So we can say that for most of the data, it looks like it is less than 5%, this margin error, with some exceptions, as you can see. So this actually is a nice way to evaluate the complete data. And this tells us that a log normal distribution looks like a reasonable approximation of the data. So what to do with this data now? So now that we have established that we can use the log normal distribution, we can basically compute the moments of this distribution for each of the vertical stripes of points, and construct plots that will have in the vertical axis the median, the normal median, that is the vertical axis in these plots, and in the horizontal plots you have the fundamental period. So by doing this, we can build a regression model to be able to predict these parameters for future use. So that's what has been done in here. And the same was done for the standard deviation of the log normal, the standard deviation of the data, sorry, because I'm going to talk about that later on. And in here we have the standard deviation in the vertical axis, and we have the fundamental period in the horizontal axis. And we again built regression models in order to fit the data. So to fit this data, basically nonlinear least squares regression was used to fit a quadratic function because it was the function that was found to fit best the data. And it was used to fit, as I mentioned before, the log normal median and the standard deviation of the strong motion duration ratio. I use the log normal median and the standard deviation because, as many of you probably know, there is a lot of different parametrizations that probability distributions have. And it depends a lot on the software that you're using. This was used with a Python library, and Python uses a parametrization that uses the log normal median and the standard deviation of the normally distributed parameter. So that's why these two parameters were selected, basically. As you can see also, for example, in the case of the log normal median, we have coefficients of determination that ranges between 0.51 to 0.8, more or less. So, I mean, considering the level of dispersion that we have, these values are actually considered acceptable. In the case of the standard deviation, we have higher dispersion. As you can see, the data is more sparse. We have a less clear trend in some cases. Maybe mainly in the last two return periods, we see that we have a trend that is different to the first 7, and also we have that in the 975 return period we have a very big dispersion, very high dispersion. Sorry. So of course, I mean, there is not a regression model that will give you a high coefficient of determination for this cloud of points because it's just too sparse. So in this case, the coefficient of determination are a bit less, are between 39.69, with the exception of the 975 return periods I mentioned before, that is 0.22. But I mean, as I mentioned, because of this high dispersion, these values are considered acceptable to predict the data, basically. So this is basically the final product of this investigation. Basically, with this probabilistic model is very handful, because with this, what we can do is that we can make random realizations of data using depending on the fundamental period of the structure and the return period. And this is very important because that is actually what we need to generate synthetic free motions. When you do generation of synthetic free motions, you need to express the strong motion duration in the form of a random variable. And when these models that we have developed here, we can do that. And that's what I'm going to show you in the next slide. In here, you have the CDFs for, you have sample CDFs for each return period for 3 different building fundamental periods that are 0.3, 0.5, and 1 second. And basically, with this, basically, if you want to have generate a realization of the strong motion duration ratio, and you have a target fundamental period of your supporting structure, and you have a target hazard level, you can basically generate the CDF as it was done in here, and use inverse cumulative distribution function method to generate random realizations of the strong motion duration ratio. Or no, it doesn't have to be the inverse cumulative distribution method. It could be any other sample generation technique. And an important observation from these CDFs is that, as you can see, the curve shifts to the right as the fundamental period increases, which aligns well with the results presented in the numerical results section, because we saw that the strong free motion duration increases with the fundamental period. So this is a way to see that the model is capable of capturing this behavior. So finally, with the conclusions, then we have that the strong free motion duration increases with both the strong ground motion duration and the building fundamental period. This is to be expected since the longer the strong shaking phase of an earthquake, then the longer the fluids of the structure will experience dynamic excitation due to this ground motion. Also, for longer period structures, it takes longer for one cycle to complete. So it also has sense to have an increase of the strong free motion duration with the fundamental period of the structure because of this. We have that the log normal median standard deviation of the strong motion duration ratio can be represented by a quadratic function. And regarding the strong motion duration ratios, we have that for the log normal median values ranges between 0.1 and 1.25, indicating in general that there is a tendency in having longer strong motion duration values than ground motion duration values. And this has complete sense due to the reasons that I mentioned before. Regarding the standard deviation, as I mentioned also before, it exhibits a high dispersion and a less clear trend in comparison to the normal median. For the majority of the ground motion return periods, there is an initial decrease of the standard deviation values until with the building fundamental period until a lower bound value is reached, after which the standard deviation tends to increase with the fundamental period. That is more or less what I showed you in these plots over here. As you can see, for most of the cases, I don't know if you can see my mouse point, but I mean, for most of the cases, we have like an initial decrease with the fundamental period, we reach a lower bound, and then it starts increasing again for most of the return periods, with the exception of the last two. And finally, an important observation of this, very important clarification, is that this model was developed for a medium to high far field seismicity site on firm ground in Europe, which means that this is representative for the European region. This needs to be validated and may have to be modified if for different sites that have different seismogenic characteristics. So that was the whole presentation. Thanks a lot for listening to me. I hope that I didn't bore you to death. And so if you have any questions, I'm happy to try to answer them.
Okay, thanks, Derek. Very nice presentation. It was a little bit in line with what I had imagined you were going to speak about. So do we have any questions or comments from anybody attending? Nope. I think
I could do
yes.
I could do a couple if everybody else is shy.
Yeah, I have a few of those as well, but go ahead, Andres.
Okay, so hey Derek, it was really nice presentation. Really good work. I'm really digging this like data analysis kind of situations. I'm running through a lot of those myself. So I had several questions. One of them is, I don't know if I missed this at the beginning, but why exactly are you focusing on the duration, right? Because I feel like this is a question, like a problem that is also for other intensity measures, but like why duration?
Yeah, you actually missed that part. That was the fun part of the presentation.
Oh yeah,
so,
I'm sorry.
Yeah, no worries. So yeah, basically I'm focusing on duration because, for example, basically the main objective of my research is to establish a framework to quantify seismic performance factors for non-structural elements. Right now, there's only one standard that addresses this issue, and it's for structural systems. That is the FEMA P695. It doesn't address it for non-structural systems. And the problem with the non-structural systems is that because we have this additional layer of analysis that we need to, for example, in order to have fluid motion, we need to first perform a nonlinear time history analysis of the structure. So it complicates things a lot. And it basically means that if you want to use like a brute force approach, like the FEMA P695, to do just all the analysis for all the buildings for which you want to assess performance of non-structural elements, it makes the process unfeasible because then you will have a crazy number of analyses. Here, for example, in this slide, you can see that for a 100 reinforced concrete building population, if we want to assess the non-structural elements performance, we will have to run more or less 11,000 analyses per Harshad level. So this makes the process very laborious and unfeasible in most of the cases. So we want, part of my research is to develop a methodology to use synthetic fluid motions in order to construct these synthetic fluid motions in a way that they're representative. A few of them are representative of the total ensemble of fluid motions, and in this way we can reduce a lot the computational power that is needed for this. But the problem with the synthetic generation fluid motions is that we need a way to express the duration. And there's, until this point right now, there has not been, the duration of fluid motions had not been investigated. So that's why basically we're doing this.
Okay. It was a missing component then.
Yeah.
Okay, I get it. Another question is, when you use for your regression a quadratic equation, aren't you worried what's going to happen outside of that range? Because you have periods that go between 0.2 and 1, and if you try to that would be the limit of what you can use with these equations, right? Because if you extend that, I mean, do you think that this relationship, the quadratic equation, is going to continue maybe above those period ranges?
No way to know. I mean, and that's actually a limitation of the study, as you mentioned. I mean, we're limited by the range of fundamental periods that we investigated. But yeah, I mean, I wouldn't dare to make to say that you can just assume that the quadratic relationship is going to continue outside these ranges. I think that is it will be very, what's the word I'm looking for? Very brave. I mean, I wouldn't do it.
Yeah. Okay, that's what I was thinking. Yeah, maybe lastly, have you guys considered using, you have a lot of data, like using a machine learning model and trying to, see how this works and everything? I mean, it's the fashion now.
Well, I mean, actually, it depends on what you mean with machine learning, because I mean, actually, regression models are a type of machine learning.
Yeah.
So, I mean, I think the machine learning concept is very misunderstood sometimes. I mean, a lot of the traditional data analysis techniques are actually machine learning. Regression models are a way of machine learning. So, I mean, it depends a lot of what you mean with machine learning, basically.
Yeah, like other type of regression algorithms, that are more, I don't know, general. And because what I was thinking is that, they might be easier to, well, I don't know if that's true, but easier to prove, because like what you were saying, that when you were fitting the log normal distributions, that it was really hard to prove that was a good distribution to use, right?
It was actually that was, in my opinion, the most challenging part of the research, for sure. I mean, at least from a theoretical point of view. But yeah, I mean, the other methods were considered. For example, before doing this probability fitting and the quadratic fitting, I also explored the option of using Gaussian regressions. But at the end of the day, I reached the conclusion that for this particular case, it didn't have sense to use a Gaussian regression. So I just rejected that idea at the end. And I mean, this was the way that we found that had more sense. Because I mean, the problem also with a lot of the most robust machine learning techniques is that a lot of them produces outputs that are not practical to use. You know what I mean?
Yeah, I do.
So the problem with this is something that we were looking also for practicity. Because, for example, if a Gaussian regression is used, the output is very difficult to use. I mean, it cannot be interpreted by a person that doesn't have a strong background in data analysis, because, I mean, basically you need to deal with the correlation matrices and a lot of stuff. I mean, people that just don't understand. So also we were looking for practicity, and in this way we can actually just produce functions that are very, very easy to understand and to use for even practitioners. So this was also an important point of this.
Yeah, that makes a lot of sense. Okay, that's it for me. Thanks.
Yeah, sure. Thank you.
Hello,
Andres.
I have a question if anybody else.
Sure, go ahead.
So I'm joining from Istanbul. I am a PhD student at Özyeğin University. I came across this webinar by luck yesterday morning, thanks to my thesis supervisor. So I am at the beginning of the PhD, but we will be working with non-structural elements as part of our research. So bear with me. Like I said, I'm at the beginning. I'm still learning, but I realized that FEMA and HAZUS has some values for all these, almost everything in the world. But it seems like you've said, it seems like these values are coming from sort of an engineering judgment, and they don't have a solid base. Am I right?
Yeah, that is actually very true. I mean, this is a big problem with non-structural elements. I mean, this is funny because I mean, this was also a big issue at this time with the structural systems, with seismic performance factor structural systems. After the FEMA P695 was published, I mean, this issue got better because I mean, since this standard gives a standardized way to actually calculate performance factors, it makes the process more reliable, more or less, you know, and it makes it makes that the use of these factors has a strong theoretical background. In the case of non-structural elements, this is not the case. I mean, I know for a fact that there are very few seismic performance factors that for non-structural elements that they have a rock solid basis. You know, I think the only one that I remember right now that I think is very well documented is for light partitions, because I think it was a study was done in the University of Buffalo by Professor Firatore actually. But beside this, I don't remember, or I'm not aware of any other seismic performance factor for any non-structural system that was developed with a strong experimental campaign, you know, or something. They're just mostly based on engineering judgment or by experience of what have seen, what it have seen, been seen in earthquakes, in reconnaissance reports and stuff like this. Yeah.
Another question is, when you say non-structural elements, what's your limit here? Because sort of sky is the limit there. That's what I understood by studying. Because I'm thinking of working on structural, non-structural part, but at the same time, it might be industrial building. So we might get into the content of the building as well, which is the machinery, which is also non-structural, but sort of fitted to the floors or the walls of the system, which may get a big damage as well.
Yeah.
So in your case, I think it's buildings you are more focused.
In this case, basically, yeah, the focus is on buildings, definitely. I mean, also the issue, well, this is a big issue, and this is one of the things I mentioned, sorry, at the beginning of the presentation as well, is that with non-structural elements, we have the issue that the archetypes are much more variable than the ones for structural systems. As you were saying, for example, the geometric characteristics of a pipe ring, for example, is very different from the one of a partition wall or for mechanical equipment or whatever. So, but however, they all have a common characteristic, most of them, and is that they are usually anchored to the structure. With the exception of the content, as you were mentioned. The content usually, sometimes depending on the classification system that you use, is not actually considered a non-structural element, it's considered a content, basically. Because of that, because the content is not anchored to the structure, so it can move more or less freely during a seismic event, which actually alters a lot the behavior, because I mean, it's not the same at all. So yeah, basically I would say that this was developed basically for buildings and for anchored non-structural elements, probably I would say.
And last question, sorry.
No worries.
So I assume this is a very small part of your study, and is that right? So I assume that I will just Google your name, and hopefully there are some papers coming in, so that I really want to read your work, because I think I may need help in a sense. Because in non-structural elements, like you said, the fragility values, I will be dealing with seismic after fire, and there are many things that I'll be dealing with. So we set the limit to the sky, and soon in the maybe third year of PhD, we're gonna come lower. So I assume, are you at the end of your PhD? So the papers are coming in soon, so that we can follow up on the work in more detail?
Yeah, Mo, thanks a lot for the comments. I mean, well, first of all, I'm in my third year right now. I have 1 year remaining. There is still the publications that we have submit. They're still under review. There's 2 of them that they have already been reviewed, and we receive a positive review. But we need to address the comments. So I mean, I don't think they will be out until at least, I don't know, a couple of months at least, I would say. But if you're interested, also, I mean, we have a non-structural research group here in Pavia, from which I'm part actually. It is managed by Professor André Firatro, and we have several students in there. And we have a website. So I mean, if you just
you
Google,
said Andre Fletro, you said?
yeah.
Oh, okay.
I mean,
so he's from Canada, right? Montreal.
Yeah, he's actually my supervisor. So I mean, if you Google non-structural elements research group in Pavia, you're gonna find the website of our research group, and you can get plenty of information in there.
Okay, thanks a lot, and
That's
thank you very much. It was very good. It went a lot into it, I assume.
Thank you.
Okay, thanks. Yeah, so those links and that information should be linked to. We can put it in the description of the other video and so on. But yeah, Google may be the most direct option. Derek, I had 1 or 2 questions I was going to. One was a question, one was a comment. I'll start with the question. So in your, what were you calling it? The strong motion duration, SMDR. So this ratio, this factor that you're describing throughout the research, it's essentially a ratio of you had a slide, I think, where you were showing the durations and the various intensities. So, but this would essentially be, I think it was the next one. Anyway, it doesn't matter. Essentially, you're looking at the area's intensity of the ground motion versus the flow response, right? So
yeah, correct.
You're looking at the accumulation of that response. So essentially, what you're doing is you're comparing a duration of PFA and PGA, right? So like the peak ground, not peak ground acceleration, but ground acceleration. So GA and FA. So the accumulation of those durations.
Yes.
And that's fine. I mean, that's a perfectly good way of starting. But given that some non-structured elements may have vibration periods which are not very rigid, so they could be very flexible, do you think that this could be something you could extend to, let's say, spectral acceleration, so the response at higher periods, not floor acceleration, but the response at 1 second, for example? And would that be something you would anticipate, see some value in? And do you think it would make a difference? It's a very big question, I know, but it's a curiosity.
Yeah, it is a good question. I mean, but I mean, to be quite honest, I mean, I don't know. I don't have an answer. This is something that we'll have to look into it, you know. I mean, right now, I mean, to be quite honest, I mean, we didn't consider other intensity measures because, I mean, we were just focused on the duration because it was the one we needed to, you know, to move forward, basically.
Sure, and it makes sense.
But,
like PFA is the go-to acceleration measure for non-structural elements in any case.
But definitely, I mean, I agree with you. This is something that it could be investigated, you know, ahead, you know, more ahead in time for sure.
And the other one was the comment I had. So I think it was one of the last conclusions that you mentioned, or the terms and conditions of the work. You said that this was evaluated for European ground motions on a certain seismogenic sources and so on. So basically, you've done this for one case study, one set of ground motions, one location, I think.
Yes.
So the results will depend on that. Given that this would just be a comment or suggestion for maybe future work, given that we're talking about duration here, duration models in ground motions, selection and so on, the GMPEs, if you want to call them that, would they tend to be correlated well with magnitude. So the bigger the magnitude, the higher duration. There are other parameters, but magnitude is a big player in that. So given that your study is based in central Italy, in Cassino, if I recall, the magnitudes are typically not that high there. So it could be beneficial for you if you want to try and see some outliers or see some different trends in like longer ground motions, to maybe look at places like Japan or New Zealand that would have much higher magnitudes, or South America, for example, so that you will get much longer ground motions, and maybe you could start seeing different factors for your
For
swim,
sure.
for your ratios then with the floor motion. So just a suggestion, because you don't have that high magnitude in Europe.
Yeah, I completely agree. I mean, and this is something that we discussed thoroughly. I mean, several times within our research group. I mean, at the end of the day, for example, I mean, this was done for, as I told you guys, for a medium to high seismicity in Europe, you know. But I mean, at the end of the day, the European hazard is not that high as compared to other places in the world, you know. As you mentioned, New Zealand, Central America, North America, you know, there is a bigger hazard in those ones, Japan as well.
For sure.
And for sure, this is, but I mean, at the end, also I believe that this is a very good start, because this is something that has not been done so far.
Mm-hmm.
So I think it's like a very good first step, and
Sure.
it sets like a way of how to do this. And for sure, I mean, I believe it's very important to basically explore how this relationship is in other seismogenic regions with longer durations, for sure. I mean,
exactly.
That's why I put that in the end, because it's an important limitation of the study, you know.
Sure. It's just an extension, like the results you have, you could just put more data on top of it, just coming from a different source.
And also I think it's very nice, because it's a very nice research area, you know. There's a lot of things that can be done in this area.
Yep.
And I actually hope that after this, after it gets published, if it gets published, because you know, you never know. But I mean, if it gets published, I hope that the other people will start looking into this with more detail, you know, for sure.
Yeah, for sure.
Mm-hmm.
Okay. Anybody else? Any question or comment? Nope. I guess not. Last one, and then we'll wrap it up. Ductility and degradation. What are your opinions on this?
In the non-structural element or in the structural system?
In the structure.
In the structure. Well, that is actually, for example, if you see, let me show you some plots here. Where is it? No, I don't have that plotting here, I think. Well, no, I don't have that plotting here. But no, but actually you can more or less, I mean, one thing that you can actually say is that as you have higher ductility demand, you have higher degradation, of course, in the structural system, your period will lengthen more or less.
Mm-hmm.
So, of course, that is not, I mean, it is quantified in here, because, I mean, for the higher return periods, for example, for the 470, for the three last ones, I would say there is some yielding in the structure. So that model should be capturing that. But at the same time, it doesn't capture the effect of I mean, it just considers the fundamental period, elastic fundamental period, you know what I mean?
Yeah.
So, I mean, another possibility of research is looking into the lengthening of the period for these high hazard levels, you know?
Sure.
But I believe, I mean, in my opinion, what I feel that is happening is that for the higher hazard levels, because we have this lengthening of the period due to inelastic action, probably the strong fluid motion duration, I would expect it to becoming higher because of this.
Mm-hmm.
And it is actually happened, because if you see, for example, these plots, there is also a slight increase of the mean values with the return period. And I believe that is the reason, probably.
Sure.
Mm-hmm.
Yeah, it's good. No, they're all things to look into. But as you mentioned, these are just some initial first steps, and different things can be looked at. So yeah, sounds good. So okay, so thanks again, Derek, for a very nice presentation. So and thanks to everybody who's joining. Everybody is quietly listening in with their videos off, so not disturbing. So we'll wrap it up here. So as I was mentioning before, we'll put this video online, and everything will be available. So if anybody wants to see it again or get in touch, everything will be up there. So yeah, that's it, I guess. So I'll stop the recording.